So we've seen previously how we can represent all linear transformations in 2 dimensions using this 2 by 2 matrix A, B, C, D. And if we apply that to a coordinate x, y, then we get the image coordinate ax plus by, cx plus dy. So that is the x coordinate of the image coordinate, and this is the y coordinate of the image coordinate. Now what we could do here is if we multiply both sides by the inverse of this matrix, so if I multiply the left hand side here by the inverse matrix, then that will cancel this matrix out and just leave me with the original coordinate, the original matrix representing the original coordinate. And on the right hand side over here, I have got the inverse matrix multiplied by the image coordinates. So basically, if I want to work out the coordinates of the original point, all I have to do is take my result and multiply it by the inverse matrix. So let's see that in an example. So here we have we're told that the image of triangle T is this coordinate, is this triangle here, so T dash to represent the image. And I want to find the object if it was the matrix 4, -1, 3, 1 that transformed triangle T to give the image. So if I first work out the inverse of this matrix, if I want to undo the transformation to get back to the original triangle, to get back to the object image, then what I want to do is find the inverse of this matrix. So remember how we find the inverse matrix? We work out the determinant. So the determinant in this case is 4 times 1 minus -1 times 3. So 4 plus 3 is 7. So the determinant of this matrix is 7. And then we flip the A and the D around and change the signs here. So we'll have the 1, 4, changing the signs, so we have 1 minus 3, and we divide by the determinant. So this is our inverse matrix. So this is what we are going to multiply by each of these coordinates to get the original coordinates. So that's what I've started to do over here. This coordinate here is the coordinate 4, 3. So if I do the inverse matrix times 4, 3, so don't worry about the 1 over 7 to begin with. We'll do 1 times 4 plus 1 times 3. So 4 plus 3 is 7. Divide by 7 is 1. And then minus 3 times 4 plus 4 times 3 is 0. And obviously 0 divided by 7 will still be 0. So the point 4, 3 has been was originally at 1, 0. When we apply this matrix to the point 1, 0, we get this point. When we apply the inverse to this point here, we get the original point 1, 0. If I now do the same thing for this coordinate here is 4, 10. So again, if I apply the inverse matrix to that point, so 1 times 4 plus 1 times 10 is 14, divide by 7 is 2. And minus 3 times 4 plus 4 times 10 is 28, divide by 7 is 4. So this point here came from the coordinate 2, 4. So 2, 4 is there, roughly. And then finally this point down here is the point, now it's the point minus 4, 3. And if I do the same thing for that, I find I get the coordinate minus 1, 0, which is there. So I can see that the original triangle looks something like this. This is triangle T here. So there we go. So basically, if you want to work out the original coordinates before a transformation, all you need to do is multiply by the inverse matrix. Second example, we've been given matrix A here. First part of the question says to give a geometrical interpretation of the transformation represented by A. So just remember that this represents what happens to the coordinate 1, 0. And this represents what happens to the coordinate 0, 1. So this is saying that the coordinate 1, 0, if I was to draw this out, the coordinate 1, 0 stays at 1, 0. So this is invariant, doesn't move. The coordinate 0, 1, this coordinate here, has been transformed to be 0, minus 1. So this stayed the same, this got reflected down, so I think that this is representing a reflection in the x-axis. Part B, I need to show that A squared is equal to the identity matrix. So if I do 1, 0, 0, minus 1, so that's A multiplied by A. I've got 1 times 1 plus 0 times 0, which is 1. Then I've got 1 times 0 plus 0 times minus 1. Then 0 times 1 plus minus 1 times 0. 0 times 0 plus minus 1 times minus 1 is plus 1. So we can see here that A squared equals the identity matrix. And there's a reason why they've asked this question in this way in this topic. Because if A squared equals the identity matrix, then what that's saying, I could multiply both sides of this by the inverse. So if I did A inverse times A squared, and A inverse times the identity matrix, then this A inverse on the left-hand side will cancel one of these A's, and A inverse times the identity matrix will be A inverse. So what this is actually saying, what this actually means, is that the inverse matrix is the same as the original transformation matrix. That's what this is saying. The inverse is the same as the original matrix. It's itself inverse. Which, if we think back to this previous question, should hopefully make sense, because if we apply the matrix A, that means a reflection in the x-axis. And if I do that again, that's going to take me back to where I began. They are that it's self-inverse. If I do this transformation twice, if I reflect it in the x-axis and then reflect it in the x-axis again, then I'll get back to where I started from. And then part C of this question says, comment on the determinant of A in the light of the transformation. So let's look at the determinant here. The determinant of A is equal to this, which is going to be 1 times minus 1, which is minus 1, minus 0 times 0. So that's just equal to minus 1. And remember that the determinant represents the area scale factor. So it should make sense in the light of the transformation that the area scale factor is just minus 1, because in a reflection, the area remains the same, remains constant. The only difference is the fact that it's a negative 1, which is all that's doing is representing the fact that the area would be below the x-axis rather than above it. That's all that minus is representing. We're still timesing by 1, so the area is going to be the same.